Remote generation for the town of Banaba, Group 7. Power people. We'd like to welcome the team. Benjamin Robertson, Aaron Adams, Connor Scard, Justin Vong, Mason Shane, Liam Kennedy. Power people was established January 2015 for the sole purpose of being able to deliver renewable projects for communities in need. All the projects undertaken are fully funded by generous donations and government grants.
So this is the project charter for the Banaba Solar Power Project by the Power People Proprietary Limited. So a project charter outlines the project's purpose, scope, stakeholders, objectives and plan. It ensures that all stakeholders are on the same page and provides a clear, concise objective for the project. So the context and background, the stakeholders are the Power People Proprietary Limited. They're the project sponsor. The project manager is Benjamin Robertson, and the residents of Banaba, Papua New Guinea. The project start date is the 6th of March 2024, and the intended end date is the 9th of September 2024. So roughly a 6-month project. The remote village of Banaba, located in the highlands of Papua New Guinea, relies on inefficient and environmentally detrimental energy sources such as kerosene lamps and diesel generators. The absence of reliable electricity limits access to education, healthcare, and economic opportunities. Current energy sources are non-renewable and hazardous to health. The objective of the Banaba Solar Power Project is to provide sustainable and reliable solar power solutions to the residents of Banaba. This initiative aims to improve the living conditions of the community, providing affordable access to clean energy, promoting economic development and enhancing overall quality of life. This project aims to serve as a model for future sustainable energy projects in remote areas. So the project scope and boundaries will include a feasibility study to determine the most suitable electricity generation, the supply and installation of one solar panel and one 12-volt battery for each of the 15 homes in Banaba, supply and installation of wiring and lighting in each home adhering to Australian standards, supply and construction of a backup diesel generator shed to be used in construction for the solar panels as well. The training sessions for local community on the use, maintenance and safety of the solar power system, implementation of safety measures to protect residents, and monitor the system's performance and provide ongoing support for a period of 6 months. What is out of scope is electrical appliances beyond lighting and device charging, additional infrastructure not related to solar power generation and non-solar power related projects in Banaba. The main deliverables: 15 fully functional solar power systems consisting of one solar panel and one 12-volt battery in each household and communal building, LED lighting for each solar power system, training sessions and documentation for Banaba residents, 6 months of post-installation monitoring and support. The acceptance criteria: the project will be accepted when the solar power generation systems are operational and consistently supplies electricity to residents for a minimum of 4 hours per day. Local residents demonstrate the ability to operate and maintain the systems through completion of training sessions. The project is completed with within the improved budget and timeline. All project stakeholders, including Banaba residents, express satisfaction with the completed project. So some constraints on this project: the targeted budget of 100,000 Australian dollars. No additional funds are available without project sponsor approval. Compliance with all Australian standards. The availability of skilled labour, equipment and material. The weather and conditions and terrain. With it being a very remote location, roads can often be closed and flooded. That's why the project will take place during the dry season. Community engagement and participation is important, that they participate in the training sessions, and the completion date for major installations scheduled for the 9th of September 2024.
So now that we have gone through the project charter, we now reach the requirement analysis. So for here, we will go through the project's inputs, outputs, functions, environmental issues, packaging issues, structural issues, safety issues, and maintenance issues regarding this project. So first up, we have the project inputs. So the goal of this project was for all electricity to be supplied, and it had to be 100% renewable. Each dwelling was to be fitted with individual solar panels, a wiring harness, and a battery system. And initially, we will have a diesel generator which will assist in the initial setup of the site and installation, and will also serve as a backup for the medical center / tourist hub. Now, the main goal of this was to have, for its output, was to have each dwelling to have at least one outlet that could be used as a lighting source for approximately 4 hours per night at roughly approximately 900 lumens. Now, it doesn't have to be purely for lighting, can be used for different uses, but in this case, our main priority was to supply lighting to this village. So again, the functions were to supply electricity and lighting for a minimum of 4 hours per night for a small village, roughly around 15 huts, and to also have a backup emergency supply for the medical center in emergency situations, i.e. the generator. Which now leads us to 2.4, which is the environmental issues regarding this project. Now, being that the village is located in PNG, it is quite tropical, and as such, there was the issues of having the solar panels being surrounded by a lot of shaded areas due to the trees, where the proposed energy source was to be located. So this requires that proposed area would be cleared in order to install the equipment, which we would employ the local workforce to do so. And as for the backup generator, as it runs on diesel, buns that were capable of storing the fuel must be installed in case the fuel tank fails, just to stop it from leaching into the surrounding environment. But again, the main source of electricity will be solar. So now on 2.5, which is the packaging issues. Now, due to the topology of the village and access and egress to that village, as you can see, the equipment needs to be compartmentalized, packaged compactly enough to be transported along the rugged roads and thick rainforest. Our only means of transportation at this point will be vehicle access only. There is no access by air due to the topology, as mentioned before, and that all materials will need to be transported by containers to avoid mechanical lifting once the equipment has reached its destination. So it'd just be one entire lift to take the container and to drop it down on its proposed installation location. Structural issues. So the structural strength of the buildings must be considered prior to the installation of the equipment. With that in mind, it will be the solar panels on the roof or the battery system, wherever that would be located. That needs to be considered. 2.6.2, the location of outlets need to be easily accessible and also meet exclusion zone requirements for AS 3000. So this whole project has to be up to Australian standards for the safety of the villagers. As touched on previously, with regards to safety is obviously paramount to locals. With this in mind, locals are to attend a brief meeting where they'll be given basic instructions of the operational aspects of the equipment. Now, the installation of equipment, as previously mentioned before, must be to Australian standards, and of course there'll be fire suppression systems included in this installation due to the battery and diesel supply. So now we are on to 2.8, which is regarding the maintenance issues. So there must be a schedule for the maintenance of the power generation equipment with the technical skills of the local population that had to be accounted for. So as previously mentioned, a meeting would be held where the locals will be taught the operational aspects of the equipment in regards with the maintenance, obviously cleaning solar panels and regular testing of safety devices. And also in the event of lighting failure or any sort of failure, the replacement must be easily replaceable by unskilled persons. So the replacement of a bulb, essentially.
So now we have the analysis of alternative solutions. This will include our brainstorming ideas for alternative solutions, and then an analysis of 3 alternative solutions, including a grid and SWOT analysis. Our brainstorming ideas included individual solar generation systems, individual rooftop wind turbines, small-scale hydroelectric power systems, geothermal, which had location restrictions, fuel cells, which were expensive and require fossil fuels. Biomass has a environmental impact restrictions. Large-scale wind farm turbines, location and environmental impact restrictions were an issue for that idea. For the large-scale solar farm, it also had location and environmental impact restrictions. And the last idea we come up with, natural gas, which obviously was location and environmental impact restrictions. So we decided to go with the first 3, and the following will include an analysis on those 3 ideas. Our first analysis is on individual solar generation systems. So solar energy is perhaps the most well-known and widely used alternative power source, and it harnesses the sun's energy to generate electricity using photovoltaic panels. In Banaba, PNG, where sunlight is abundant throughout the year, solar energy can be a reliable and efficient power source. The installation of solar panels on individual rooftops with a battery connected will provide a supply of electricity at night for villagers. Solar energy is also a silent and pollution-free option, making it environmentally friendly. Although the initial setup costs may be high, the long-term benefits of solar energy make it an attractive option for powering the small village of Banaba in PNG. And as you can see, Banaba has an abundance of daylight hours to harness that solar energy. So some advantages and disadvantages of individual solar installations. Advantages include sustainable and requires little or no maintenance. It improves individual access to electricity, and it is a small upfront cost than other renewable systems, and produces a pollution-free energy, making it environmentally friendly. Disadvantages include the small-scale clearing for the panels if required, and it will only produce power during daylight hours. Our second idea was individual rooftop wind turbines. So wind power is another alternative power source that can be considered for Banaba. Papua New Guinea experiences strong winds, especially in coastal and mountainous regions, making an ideal location for wind turbines. Wind energy involves converting the kinetic energy of wind into electricity through the rotation of turbine blades. The installation of wind turbines can provide a supply of electricity even during periods of low sunlight or dry seasons. Wind power is also a clean and renewable source of energy, producing no greenhouse gas emissions. However, the main drawback of wind power is its variability. While the wind is generally strong in PNG, there may be periods of calm or low wind speeds, leading to intermittent power generation. Some advantages and disadvantages of individual wind turbines. Advantages would include it can generate when cloudy or at night, minimal maintenance, and it has a small footprint when installed on rooftops. Disadvantages, maybe intermittent production as wind isn't always consistent, expensive repairs, environmental impacts when manufacturing and installing, and potential noise and visual impacts. Our third solution is small-scale hydroelectric power systems. So hydroelectric power is another viable alternative power source for the small village of Banaba in PNG. The country is rich in rivers and water bodies which can be utilised to generate electricity. Hydroelectric power plants harness the energy of flowing water to produce electricity. A small-scale hydroelectric power plant can be built near a river or stream to provide a constant and reliable source of electricity. The initial setup costs for hydroelectric systems may be higher than other options, but the long-term benefits are significant. Hydroelectric power is renewable, emits no greenhouse gases, and has low operational costs once the infrastructure is in place. Additionally, the water used for power generation can also be used for irrigation, further benefiting the community. The advantages of this solution include generation for 24 hours a day, minimal maintenance besides cleaning pipes, and clean renewable energy source. The disadvantages include initial setup costs are much higher than other systems, limited viable water supply within the area, and small-scale setups are often less effective. So the next few slides are our grid and SWOT analysis of the alternative solutions. The first analysis we did was a grid. So we conducted a grid analysis of alternative solutions to assist in deciding on the most appropriate power generation source needed for the village Banaba in Papua New Guinea. 3 main alternative solutions were scored against each criteria from 0, poor, to 5, excellent. And these solutions selected individual solar generation systems, individual rooftop wind turbines, and a small hydroelectric power systems. The criteria to be considered were weighted 0, not important, to 5, very important, and they were as follows: cost, environment, safety, generation reliability, load, and maintenance. So in the first table, you can see we have scored each solution against each criteria. And in the second table below, you can see what we've weighted each of those criteria at, and then we've multiplied the score by the weight to give us the totals for each solution, with solar power coming out on top at 81. Our last analysis was a SWOT analysis for each alternative solution. These were an evaluation of the strengths, weaknesses, and opportunities and threats associated with installation on an individual basis. Overall, the individual solar generation system had more strengths and less threats. The small-scale hydroelectric power systems had more weaknesses and threats than the other two, and the individual rooftop wind turbines had more weaknesses than the solar generation systems.
Number 4, project risks. A hazard. A source of potential damage which can cause harm, damage, or have a negative effect on persons, property, health and safety, or the environment. In layman's terms, the hazard is the thing that is going to affect the project or hurt the people. So Risk. The chance or probability that a person or a project will be harmed or experience an adverse effect if exposed to a hazard, including situations with property or equipment loss or harmful effects on the environment. In layman's terms, a risk is the probability of the hazard coming true. On the left, we have the likelihood of the event occurring. Rare, unlikely, possible, likely, almost certain. And across the top is the consequence of that hazard happening. Insignificant, minor, moderate, major, or catastrophic. And by working across this chart, this is how we rank the assessment of each hazard as we come across them. 4.2 Risk Assessment Table. Project not meeting our timeline. Rating, high. Controls implemented. Have a project timeline with milestones. Ensure delay time is built into each stage. So after the controls are implemented, we have a moderate rating. Unable to get equipment to site. Extreme. Find a logistics company that is familiar with completing deliveries in the area. We still have a high rating, but it has come down. Availability of equipment and parts. Ensure communication with vendors is kept open so that a pivot can be made onto a new supplier if issues are encountered. No availability of skilled labour for the project locally. Labour will be sourced in Australia and will be fly in, fly out. Weather events causing project to stop. Project to be timed for the dry season, June to September. Consultant or contractor delays. Communicate regularly and put late penalties into their contracts. Scope creep. Original project not to have any added scope, any new deliverables to be a new project with its own timeline. Cost of materials rising, causing budget blowout. All high value materials and contracts to be quoted, paid, received by a certain timeline. Environmental issues. In-depth environmental survey to be performed in the early stages of the project and outline any potential impacts or issues that need to be planned for. Local people unable to operate the equipment. Training of the local people will be included in the project and extra low voltage to be utilised. Local communities not engaged and scope of works not clearly agreed on. Visit will be planned well in advance of the project to discuss any cultural heritage sites and agree to the location for the building works of the project. Also have community information sessions.
Okay, so now let's discuss the technical specifications of the Banaba generation project. For time purposes, the information in these slides have been kept to key relevant points. And we're going to start off with a few broader points actually around the system that provide context to it and reiterate the design points that we have tried to emphasize. Okay, so this is a distributed extra low voltage system. And this is important for a couple of reasons, but possibly the most important reason is the skill level of the locals. This is regarding maintenance and repair. Modularity, flexibility, and plug and play off-the-shelf componentry has been prioritized, and this is entirely for product packaging and componentry shipping requirements. And the last 2 points that I'd like to speak to overlap the first 2 points, but that's the design requirement for a hardy maintenance-free design. Isolation of the village means that fragile and maintenance heavy systems will have unacceptable downtime over its lifespan. Okay, so let's have a quick look at our state transition diagram. It's a very simple system, as we can see in the diagram. It functions by the sun shining on the panels, which output 200 watts at 12 volts to the solar controller. This provides battery overcharge protection, and it regulates the current voltage flow to battery. The battery is charged with this regulated DC via the battery protection, which is inbuilt into the battery box, as long as the isolator is closed. The battery then feeds the DC supply to the accessory protection, which is built into the battery box as well. And as long as this protection has not operated, this will energize the light switch. Finally, when the light switch is turned on, our LED light will produce the required 900 lumens for 4 hours. Okay, so getting into the nitty gritty of it a little more, let's start with our solar panel and our solar controller, the specs for these. So solar panel power rating, 200 watts. Obviously, this is a 12 volt system. The panel construction, it needs to be a rigid type panel, not a flexible type. This is both for packaging and shipping reasons. The ad hoc construction of the dwellings means that the panels need to be self-supporting. Fairly standard connectors, MC4 connectors, and 2.5mm leads required. The solar controller, the IP rating of it has to be IP67. We're aiming for waterproof for the whole system. The voltage rating has to be 12 volts, 16 amp minimum current rating to meet the output of the panel, and the lead size, the minimum leads we've spec'd for the cables, that has to be 6mm, and we'll discuss that further when we discuss the leads. All right, now onto our battery box and our batteries. Once again, the battery box, we see the IP67 rating. It's the minimum requirement that we have for the whole system. The internal box size, this is based on standard battery sizes, 425 by 240 by 185 mils. The box protection functions, so for the battery, on the battery side, it needs to have a battery isolator and outlet over current protection. The connector type, we need 50 amp Anderson plugs to feed from the solar, and then potentially also for future upgrades, 2 USB outlets and 1 automobile auxiliary accessory outlet. The battery itself, we've asked for lithium ion, 12 volts. It has to have a requirement of 2000 cycles. This is to meet the minimum lifespan of the system, and also we need a amp hour rating of 80 amps. 80 amp hours, that is, for the battery current. And the battery dimensions, obviously, it aligns with that of the box. All right, cables and connectors. So we have asked for 6mm cables. This is just to account for any potential for voltage drop we have over the system. Insulation XLPE. This is a 2-core and sheath type cable. We have a requirement for differently identified cores using red and black coloring for each of the cables, each of the cores, that is. The cable connectors, MC4 at the solar panel end and 50 amp Anderson plug at the battery box end. This is obviously due to the polarity sensitive nature of an Anderson plug. Weatherproof covers to be installed over the end of the Anderson plugs. The cable protection is to be 25mm heavy duty conduit. And the site generator specs, it's a diesel generator with an output of 240 volts, and we've asked for a 3 kVA. This is to be able to run things like a site fridge for the people installing and teaching the locals on commencement of the project, as well as to be able to charge batteries for power tools. Alright, so now we're on to supporting equipment and handover training. So part of the handover training, an important part of that, is going to be basic fault finding and repair training. As we've touched on, it's a very simple system. It's all plug and play, and it's extra low voltage, so it's able to be worked on. The maintenance instructions are simple tasks like ensuring that the battery protection still functions, the isolator is still operable, and that solar panels are appropriately clear to be able to generate what they need to. Safety training, so what to do in emergencies and how to correctly operate the system. The generator and container,
they are both to be left for the community. So the community can utilize them in emergencies or however they best see fit. Fire suppression is to be left for each of the installations and for the generator. So that's a fire extinguisher for the generator, and fire blankets for each of the installations. The fire blankets to be able to be large enough to cover the solar panel as well. And then obviously spares, so that in the event of a breakdown, repairs can be implemented without getting spares from the next big major town.
A work breakdown structure is a project management tool that takes a step-by-step approach to complete large projects with several moving pieces by breaking down the project into smaller components. The work breakdown structure in front of you is the step-by-step process for our electricity project in Banaba, a small village in remote PNG. As we move through the slides, I'll go through the work packages and activities to give you a grasp of what we plan on achieving in this town. As you can see in the tree structure in front of you, there is a total of 5 packages which are coloured grey and 11 activities which are coloured orange. The numbering dictates what package each activity belongs to. For example, activity 1.1.2 belongs to package 1.1 as the first 2 numbers for each are the same. Another example, if I had package 1.3, then a corresponding activity would be 1.3.1. The 5 packages are 1.1 planning and design, 1.2 transport, 1.3 site setup, 1.4 installation, and 1.5 testing, each with their corresponding activities below, which once completed fulfill the package requirements. Next 3 slides are the work breakdown structure dictionary, which is where the details of the tasks and activities are located. This content includes a description of the activity, the responsible person, the duration of the activity, labour costing, fixed costing, and any predecessors before activities can begin. The total costing of our project equates to $25,050 in labour costs and $94,290 in fixed costs. And we aim to have all the works completed in just under 2 months, a total of 57 days, under the supervision of a group leader. As can be seen, each package is white in colour with the same labelling as the tree structure and displays the package's total timeframes and total costings for all corresponding activities. It also has a description of what is involved and a responsible person who is the coordinator of that package. The activities are yellow with the same information layout but more specific to each activity. The first package is 1.1 planning and design with 4 activities. 1.1.1 requirements analysis, 1.1.2 project risks, 1.1.3 costings, and 1.1.4 procurement. This is the initial package of works where we take into consideration all factors to come up with the best plan to make this project as safe and efficient as possible and make sure we can get all equipment needed in the time frame required to complete the project. The second package is 1.2 transport with only 1 activity, 1.2.1 truck transport. This is the transport of all equipment to site via trucks, as we have limited access to the town and trucks were the best and most affordable option. The third package is 1.3 site setup with 3 activities, 1.3.1 generator shed, 1.3.2 distribution line / poles, and 1.3.3 control / protection system board. This package is the construction of the generator shed to house the generator, safety controls and its corresponding safety equipment, and to prepare all dwellings for power with the running of distribution lines throughout the village. The fourth package is 1.4 installation with 1 activity, 1.4.1 generator install and connection. This is the installation and connection of the generator to the safety system and distribution lines so electricity can be sent out to the village to provide power. The last package is 1.5 testing with 2 activities, 1.5.1 electrical mandatory testing and 1.5.2 protection systems testing. This is to test the system and make sure it is up to and complies with the electrical standards and regulations and is going to operate as intended, and if faults occur, the safety system will protect and operate correctly to reduce the risk of harm to the villagers and the system. Once all packages have been completed, the project is finished and ready to hand over.